And we've said that the job of a BGP router is to process different inputs that come from neighboring routers or from its own configuration. And it typically does it by screening a number of criterions in a certain priority order. And typically, or by default, it is this order given here. What we will see now is how in detail this works. This is where we stopped last week. So we consider a toy example where we have two ASs, X and Y. In AS-Y, we have two prefixes, 10.1/16, 10.2/16, that are advertised by the blue boxes that are BGP routers to other BGP routers in the peer domain here. We zoom on R1 and look what happens. So when R1 receives from R3, which is this neighbor here, it receives the information, R1, R2, R3, yes. It receives those two routes. So note that 10.1 is perhaps directly connected or in the vicinity of R3. 10.2 is not, but depending on how you configure the routers, you may wish that one BGP router advertise to a peer, to another AS, all the routes that are inside the AS, which is what is done here. So R1 receives the information about those two network prefixes. There is one field that we discover here is called the next hop. Next hop is the IP address of the router or the place to which send traffic that go to this destination. In this case, it is the IP address of R3 on its link to R1. And we mentioned last week that such an IP address, such a next hop, has to be internal to the domain that receives it. So here it means concretely that the links between those two domains, which are shared between the domains, are considered as internal by both domains. For example, the routing protocol inside domain X, if it's OSPF, must have a stub prefix, for example, for this domain here. Since R1 has received only this this route from BGP, and if the policy accepts it, which we assume here is the case, it will pick it as the best. There is no other one. Then, the job of R1 is not finished when it has just selected the best route. It also has to repeat to its BGP neighbors the best route it has. Also, if policy accepts it, but here internally it does, like practically always. So what are the neighbors that R1 is concerned with? Here it's R2. So R2 is also a BGP router. It has a TCP connection with R1 over which they run BGP. Now, R1 will inform R2 of this route, which means that R2 knows now that there is a route to each of those two prefixes, and the next hop, which is the direction to which to send traffic for these two prefixes, is this one here. Now, assume that a similar thing has occurred at R2 in parallel, perhaps just after. R2 has received from R4 a similar advertisement as R1 has received from R3. So R2 has received a route which is this one, the same prefix, but the next hop is different. The next hop corresponds to the link on the right of the figure. Now, the same thing will happen. R2 will send to R1 over BGP, internally, iBGP. It will send this route information. Now, R1 really has a choice to take, because for each of those two prefixes, the ones marked in red here, there are two routes. One that goes this way, one that goes that way. So which of the two new routes will BGP at R1 select as the best one? I close the poll. And it's a tie with a small advantage to B, but perhaps this is what you would prefer. You would prefer that the route to this guy goes with this next hop by R1, right? Perhaps that's what you want. But this is not what will happen, at least not without any additional attributes, because if we come back to the decision process, which is given here, this is what will be tested in this order. So let's go here again to all those details. So R3 to the prefix 10.1 has two routes. So it will look in detail at whether there is a weight. There is no weight, there is no local pref, so those priority fields do not apply. And the next criterion is what is the AS path. Now the AS path is the same length, it's just Y. And so they are also equal. The next thing is lowest med. Med is a priority field that we have not indicated here, so it doesn't apply. And then the last criterion, it says that eBGP is preferred over iBGP. So this route has been received from R2 over BGP, but from an internal neighbor. So we say it's over iBGP. Whereas this one has been received from an external neighbor. So the one received from an external neighbor, if there are with this rule, has priority, which means R1 will prefer the route it had received from R3. So among those two, R1 will prefer the first one. And the same will happen to the second route, because the second route also comes from for the second route, we will prefer the one that comes from R3, which means that those two red routes are considered less good by this BGP router than the one it had before. As a result, it will not pick any of those as the best ones, so the correct answer is D here. Right. This is what happens by default. If you want a different behavior, you have to play with some of the attributes, which is what we will see a bit later. So let's continue to see a slightly different example. So we zoom again on R1, but now we assume that in the domain on the top there are 3 BGP routers, and that the physical links are given by the plain lines, and the dotted lines indicate TCP connections that are used for iBGP. Right. And we assume here things are okay in the sense that there is a routing protocol in each domain to, for example, make sure that this connection from R1 to R22 works here. We assume also that there is now a slight difference in policy in R3 in the sense that R3 has been configured such that, in domain Y, such that R3 advertises only the prefix 10.1, which perhaps is directly connected to it, and R4 advertises only the prefix 10.2. So it's a different configuration. We'll talk about that later. It's called, in the lab you will see that you have to decide which BGP router advertises or originates into the system which routes. So here we've changed the configuration, and every BGP router announces only the thing that's local to itself. Right? That usually is not the case, but it could be the case if anyhow you want to, if the link, if this router is dead, then this prefix is non-reachable, perhaps because they are physically connected to the router. That would be a case where it's acceptable to do such a thing. Otherwise, if things are more general, you don't want that the death or the crash of one BGP router makes an entire route unreachable. So in that case, if this router crashes, it's the only one that's sending the information on 10.1 into the internet. If this router crashes, 10.1 becomes unreachable. But let's assume this is what it's done, and let's see what happens again at R1. So first, when R1 receives this information, 10.1, it keeps it because it's the best, and the next hop, observe, is this one. and it will inform its two BGP neighbors inside the domain of this new information. It will send to R21 and R22 the information that this prefix is reachable here, right? Assuming everything is accepted, policy is not filtering out any of those advertisements, right? Now, the same thing has happened, probably in parallel here. So R22 has received from R4 a similar advertisement, 10.2.16, and is now repeating it to R1. So R1 receives from R22 a route to 10.2 with next hop 2221, which is this one here, right? Now, what will happen? Of course, R1 accepts the update and stores it and runs the decision process. Now, it's the first time we see this route, so same thing, there is no alternative, it's automatically the best. Now, R1 does not forward it to R21 or R22 because of the rule that whatever you have learned over IBGP, you don't repeat over IBGP. Because R21, well, there's no point sending it to R22 because it comes from R22. And there's also no point repeating it to R21 because the assumption is that there is a full mesh inside the domain of all BGP routers. So R21 will hear that from R22. So it's not repeated here. It's also not repeated to R3 because this is a route that has the domain Y. So if I send it to R3, I would need to add my own domain X, but I would be sending to Y a route that comes from Y. So it would be creating a loop here. So I don't want to create an AS loop, because obviously you don't want to send to an AS information that comes from this AS, so it's not repeated either. So nothing else happens, right? Now, sooner or later, the same will happen with R21. R21 has received, which is a neighbor of R4 as well. So R4 has two external BGP neighbors. R21 will receive the same route with a different next hop, which corresponds to this link here, 3331. Right? Now, what will R1 do when it receives this route? Will it keep it or will it prefer the old one? I close the poll in 5 seconds. The majority says yes, and it's the correct answer. So here the decision process will go through the same kind of rules, through the same steps as in the previous case, but now both are received from IBGP. So the clause that says eBGP is preferred does not apply, so we go to the next criterion, and the next criterion says shortest distance according to the IGP, shortest distance to next hop. This means here R1 will pick of those two routes, this and that, it will pick the one that has the shortest distance to the next hop. The next hop is this or this. It's the shortest distance inside the domain X, because as we said before, the next hops have to be treated as internal to a domain. Now, I don't know exactly what the distance is, but if there is one OSPF gives the same weight to those two links, well, even in any case, I mean, this must be shorter than this one because there's only one path and it goes via R21. So this next hop is closer than this one, so it will pick this one here. So R1 will route to this, not to that, because it is closer inside its domain here. But we have made sure that we inject the routes as shown here. So this was illustrating the fundamental operation and how the rules apply and the sequence of events that typically happens in BGP and that you have to simulate in your head when you want to design a certain set of behavior for BGP. Now we will discuss about this behavior and a number of simple attributes that are used to modify it in a simple way here. Now, assume another case here. ISP1 and ISP2 are shared cost peers. That means that they accept all the advertisements for all the customers of each other, but they would probably refuse to serve as transit or otherwise. If we consider separately the path, which path will be used by packets from customer 1 to customer 2 in this case here, if we use the default settings of BGP. I close in 5 seconds. And the majority says B, which is a correct answer in this context. By default, BGP will pick the routes that go to the closest next hop. Here there are 2. So if something comes from here, BGP by default will route this way. It's called hot potato routing. You have a hot potato, you want to get rid of it as quickly as possible. So the traffic that comes here, by default, if you don't do any modifications to the attributes of inside BGP, then all traffic will exit as quickly as possible. This is often done in the internet, often but not always. It has a side effect. If both providers are applying hot potato routing, then routing from customer 2 to customer 1 will follow a different path. It will leave immediately here. So that's cause for path asymmetry in the internet. It is quite possible that when you do a ping in one direction or in the reverse direction, the packets follow different paths. And the typical reason is BGP. The decisions to route from A to B do not lead to the same results as the decision to route from B to A. Here is an example here. So in particular, we should not assume in the internet that routing will be symmetric. We saw in the previous example 2 ways of originating the routes into the internet. Originating is the word that is sometimes, not always, used for the bootstrapping of the networks into the internet. The job of BGP is to analyze inputs it receives from neighbors and propagate them or not propagate them, depending on the decision process. But at some point, the routes, and this is most of the job of BGP, but the routes have to be input into the system by some of the routers. So typically, it is done by the routers that are in the domain where those prefixes exist. And there are some subtleties here. Of course, you can always do that manually by typing into some commands into the router. We'll see how to do that in the lab, and say this router, which are the prefixes to originate, not originated. This is something that is interesting if you want to have full power. For example, in the case we saw before, you wanted R3 to originate one prefix, R4 to originate another prefix. This is a simple way to achieve this. But of course, this is error-prone, like any static configuration. Even if you write a script, you will make sure that your script changes if the configuration changes, if somebody adds a prefix into your network. So what is most often done is one of the two: redistribute connected. That means tell this BGP router to put into BGP all the routes, all the prefixes that it is connected to. So as soon as the router detects that an interface is up, it will analyze what is the network prefix of this interface, and it will send it to BGP. This is perhaps what was done in the case before, where one router was connected to 10.1, the other to 10.2. If they redistribute connected, this is what would happen. Another case, but this works only if this if all routes, this has the effect that all routes that are put into BGP are the routes that are directly connected, the prefixes that are the network prefixes that are directly connected to BGP routers. In a domain, you may have some routers that are not running BGP. So we may also use another method, which is called redistribute from IGP. The word redistribute has a very specific meaning in the context of routing protocols. Redistribute means take as input in some routing protocol what has been computed and obtained from another routing protocol. Here, IGP is, for example, OSPF. Remember that in the language of BGP, IGP means whatever interior domain routing protocol. For example, OSPF for us. All nodes, all routers in a network that run OSPF will discover all the routes, all the prefixes that exist in this router. So if you say redistribute from OSPF, that means all BGP routers will put into BGP all the routes that they have learned through OSPF. Right? Perhaps this is what was done in the example, in the case 1 we saw before, where both routers R3 and R4 were advertising in BGP all the prefixes that exist in their domain. This is the behavior you obtain if you use this method. Before diving into how to manipulate the attributes to achieve a certain behavior, we need to talk about something called aggregation. Aggregation is the fact that the number of routes, or aggregation is motivated by the fact that the number of routes in IPv4 is almost astronomical, it's close to 1 million. If you're running BGP and you're backbone provider of the internet, you will have today close to 800,000 IPv4 routes. For IPv6, you will have much, much fewer. Why is there such a difference between IPv6 and IPv4? Why are there 10 or 20 times fewer routes to be announced for IPv6 than IPv4? Any idea? If you're nasty, you could say this is because IPv6 is not so widespread, so nobody cares, so which could be a reason, but there's another good reason. If you think of the IPv6 prefixes of EPFL, ETH, switch, for example, they are all starting with the same prefix. So all the EPFL, ETH, all Swiss universities have an IPv6 prefix, which is a sub-prefix of the prefix of switch. So for the rest of the world, for IPv6, there is only one prefix to go to Switzerland academic world, which is the prefix of switch. So if you're a backbone router in the US, you see only one IPv6 prefix to route to all domains that are including that are in the Swiss academic community, including EPFL. For IPv4, and this is the desirable property, that's the principle of IPv6 address. We can aggregate them if we are served by a given ISP. There's no reason that the rest of the world knows exactly our prefix, the details of our prefix. For IPv4, this is not possible because the prefixes have been allocated in a more chaotic way, and also because the IPv4 address space is smaller, so it's more difficult to do flexible arrangements. For example, the prefixes of ETH and EPFL are not at all contiguous, so you cannot make them in a block, and between the numbers that are allocated to EPFL and ETH, there are other domains that have been allocated to things that have nothing to do with Switzerland. So it's not possible to aggregate in IPv4. So aggregation is a key issue to obtain scalability. So as much as possible, if you're a provider and you advertise BGP stuff, you will aggregate. For example, Switch will not send a prefix for each of its customers, it will send only one prefix. And if EPFL would be using BGP with Switch, then if EPFL advertises its prefix, then Switch should not advertise to the rest of the world all the prefixes that it has received from EPFL, ETH, etc. It should aggregate. So the aggregation function is a function that is typically done at the output once you have selected best routes and you have to say to some neighbors a number of best routes. Then you can decide whether you aggregate all of them into one. And ideally, you should do that always. What we will see now is what are the side effects of aggregation and a few little things that we should be aware of. Right? In the form of questions. So here, I'm showing IPv6 addresses. Remember, BGP handles IPv6 as well as IPv4. And aggregation is typically a problem for IPv6. So here I have AS1 that has a prefix, 48-bit, and AS2 has another prefix, and they are contiguous and they differ by only 1 bit, right? E and F are, they differ by only their last bit, right? F is all ones, and E is the same -1, means it's all one except the last bit, which is 0. Now, AS3 receives those two advertisements, and the question is, when AS3 speaks to AS4, can it aggregate those two routes into a single one? Is it mathematically possible? I close in 5 seconds. And the correct answer is A. That was the easy part, at least if you're familiar with binary and IPv6 address, which I hope you are by now. So this is a simple exercise on manipulating the prefixes. Now let's continue. So this guy, AS3, has aggregated, and this is, for example, the case of switch that is serving ETH and EPFL. Then when it speaks to another internet service provider, it will just pass this information to make it one. But assume that, for example, EPFL is also directly connected to this service provider. This is not the case of EPFL. EPFL would speak directly through switch, but assume it has another link because switch is not an exclusive customer, an exclusive service provider for this guy. Even though the prefix comes from switch, it might still be directly connected to another one here. So AS4 now receives 2 BGP announcements. This one, which is the aggregated prefix that covers the two, and that one that comes from AS2. Now AS2 has no reason to aggregate. It should speak for itself only. So it sends this one. Now AS4, a router, one BGP router, we don't know exactly which one, but through a direct connection to the two or through iBGP and intermediate BGP routers. If we take one router, one BGP router in AS4, it will receive those 2 advertisements with some next hop. Which one can be taken as best by the rules of BGP? I close in 5 seconds. Actually, I don't close because the majority is wrong. So I would like to ask you to think about it, and I'll give you a second chance. Talk to your neighbor. Try to convince or be convinced. I can close the poll now. I'm happy with this manipulation of votes in the election. But now the majority says C, both routes, and this is correct, because those are 2 different routes. They are not 2 routes to the same network prefix. So aggregation is done at the output, but when you receive 2 routes. Of course, if aggregation is performed inside AS4, that means a router that is behind the aggregation will only see one of the 2, and then there's no discussion which of the one of the 2 is hidden. For example, if there is aggregation, this route will not be visible. But here, if it receives both, then they are different. They are 2 different prefixes. So the take-home message is overlapping prefixes are considered as different. So the decision process does not compare overlapping prefixes. It's the aggregation process, which is post-processing, after the decision process. When you want to give more information to others, you may decide to not give all detailed information, but this is aggregation in the output, not done by the decision process. Now, if we keep both, of course, the decision process might be influenced by weights or by filtering rules that make it impossible to have one of the routes. For example, this one perhaps is not accepted, but if both are accepted, and now we take a packet from AS4 is here, to this destination, Baba-Bip, which is here, right? Which path will it follow? I close the poll. And now the large majority says B, which is correct. It will follow the shortest path. Not because it is the shortest path, but because of what? Because of longest prefix match. So if both routes are accepted and somehow translated into the domain AS4 by routing table entries, when a packet goes to this destination, it will find two routing table entries, one to this destination, one to that. But it will match the more specific, the second one. So if the second one was accepted with the next hop that is here, it will go this way. So this is what happens if you have aggregation. Or not. Here there was not aggregation inside AS4. Not aggregating means we can preserve the specific paths here. But what will happen if this link breaks, the connection from AS2 to AS4? We can analyze using the pieces we've seen so far. If the link breaks, so the connection between the two is broken, and the keep alive or the hello mechanism of BGP will detect that this adjacency is lost. So remember that a BGP router keeps everything it has received, even if they are not selected. One of the purposes is also to be able to see what is valid, what is not invalid. The thing that comes in all routers, or a router that at the end of the link here is declared invalid. And when a route becomes invalid, the decision process recomputes the routes using all the inputs it has received. So the decision process at the router here has now two routes, the one that is not aggregated, that is aggregated, and the specific one. Saying completely stupid things. Now it has lost this route, which was the only one it had, so it will simply have now no route to this prefix here. The BGP, as we have discussed, acts by updating, withdrawing, or adding messages. So inside this domain, there will be withdraw messages for this route, so that all BGP routers here will delete this route, and there will be no prefix, no route corresponding to this prefix here. But there will be a route corresponding to the prefix, the aggregated prefix, that was received from AS3, not shown here, but AS3 had sent to AS4 the aggregated prefix that will continue to exist. So when packets from AS4 have a destination in AS2, they will now match the only existing prefix, which is the longest, the shorter, this one, and they will go via S3, AS2. Right. So what is the take-home message? Well, here the take-home message is, of course, we want to aggregate, and aggregation is good here. But if you have a specific path, you can still keep it, because you will have the both properties. You will have the best of both worlds. Traffic that goes directly, if you prefer this path, if AS2, AS4 have a direct connection, probably it is because they want to use it. So you want to send the traffic as quickly as possible. But you are able to use as a backup the aggregated connection, the aggregated route. That's the end of the animation. Voila, so this is the special topic aggregated routes, which is very important in the internet because many, many routes are a subset of other routes. We'll see other examples of how this, of the impacts of this. Right now, we still need to see another part, which is how we go from BGP to the routing table. Ideally, if you think intellectually, which is not always the best exercise to do when reasoning about software, but if you think in a well-designed system, even sometimes if you read books about BGP, the ideal thing would be to say, well, we have a hierarchy of routing protocols here. We have routing inside the domain, and we have BGP routers that have the job of exchanging the information between domains. So ideally, a BGP router should be more like a server than a router. It should exchange the routes and then talk to the true routers that run OSPF to pass into OSPF, for example, the routes they have learned. That would be the normal way to do. And in some cases, we can have things happen in this way, but the normal way to do is a bit different. The normal way to do, which means Cisco, Juniper routers, and the software versions we have in the lab, they always do what is called injections, which means that all the BGP routes they have learned, they put it directly in their forwarding table. So they don't act as a server that talks to a router, they act directly as being a router. And this is called injection. So injection of BGP routes means a BGP router has learned through BGP how to go to a certain destination. It will write directly in the routing table information that leads to this destination. There are a few subtleties that we will see in a minute. Another way to do the same thing, which is the more intellectually satisfying, would be to say to the interior routing protocol, say to OSPF, all the things you have learned about the external routes. We have seen that in OSPF, you have seen in the lab, that there can be things that are called external routes, which is practically the same as stub routes. If a router running OSPF has a number of routes that it knows how to go to, and going through this router, then we can treat them as stub routes or external routes in OSPF. And this way of doing is called redistribution, using the word we've seen already. BGP has learned a number of routes, then it can say to OSPF, here are all the prefixes I have. So with OSPF, that means that all the routers, the BGP routers that also run OSPF, they have now information about how to go to some routes and will, in some sense, do the same thing as we saw in OSPF in the case of multiple areas. We saw that area border routers in OSPF know how to route to some prefixes that are not in the area that they're talking to, but they know what's the distance, and they pass this information to everyone in OSPF as if they would be directly connected. Here's the same principle of redistribution. We'll see the details after the break. Let's continue our exploration of the many features of BGP. So the topic we're discussing is how BGP informs all the routers in its domain of the routes that it has learned. One method, which is intellectually the simpler, is redistribution, and the other, which is more primitive, is injection. So let's see how both work. Let's assume in this domain in the middle, we run OSPF. We have 2 BGP routers and 3 routers in total. So the BGP routers are also OSPF routers here. But the router in the middle, R1, runs only OSPF. Right? And let's see what happens to the route 18.1/16 that has been received by R6 over eBGP, repeated to R2 over iBGP. Right? R6, if we use redistribution, will redistribute into OSPF this route, 18.1, with next hop 222. Right? OSPF takes an attribute called next hop. So via OSPF now, let's assume for simplification it's a single area, R1 and R2 will receive this information from OSPF. So R1 will know that for this prefix, you have to go to this next hop, right? And it will also compute the cost to the destination here. So R1 and R2 now have a route, in their forwarding table entry, written by OSPF, there will be a way to go to this direction in order to reach 18.1 here. So any packet to destination 18.1 will find a way because the prefix 18.1 is now present in all routers, including R1 through OSPF and R2. Now R2, observe that R2 has two mechanisms to put into the routing table this route, one that comes from BGP because it knows about it from BGP, and another one which is learned from OSPF here. This is a classical method that is used by some, but many network managers prefer not to use it. There's a number of good and bad reasons. One of the reasons is sometimes your version of the routing protocol, if it's not OSPF, is not able to handle the table sizes. Some routing protocols, like RIP, that we'll see a bit later, are made to run private domains that have hundreds, perhaps thousands of routers, so perhaps 10,000 network prefixes, not more, usually much, much fewer. And so they might not be designed to run the close to million number of network prefixes that BGP puts into the system. So that is one reason for having that. Depending also on the routing protocol, if for distance vector routing protocol, the way they work is they constantly compute new routes, and if they have a huge number of routes due to external routes, this incremental update can take a lot of time. So whenever there is a failure, such protocols may have a problem here. Protocols like OSPF were designed with this in mind. Through various mechanisms, OSPF is expecting to have a topology database, a link state database in every router, so it's expecting to have a large amount of memory. OSPF is not a cheap protocol in terms of memory footprint. And it has mechanisms to optimize also the handling of external routes. Stub and external routes are not directly handled by Dijkstra, but they are, as we have seen when we talked about multi-area, they are added after you have computed all shortest paths to all boundary routers. Then you compare the different boundary routers that give access to a given external route, which is much faster. So with OSPF, it would work. There's another reason that we'll discuss in a minute, is also conflict of injections. If you think about it in this example, the route 18.1 here, if we focus on R2, R2 will receive some information about the route 18.1 through OSPF, but also through IBGP. Normally, in a well-designed world, what should R2 write into the routing table? Should it write the information it has received from OSPF or the information it has received from BGP? Well, in my opinion, that's just an opinion, that doesn't correspond to what is done in the world. That's just my vision of the ideal world, which is not the real world. Ideally, these routes are external routes. This route 18.1 is an external route. So putting it into this domain is the same problem that you have in OSPF or in BGP, which is how do we bootstrap the routes? How do we make them known to the domain? And normally, who bootstraps a route is the systems that are directly connected to them. In OSPF, we've seen that we redistribute connected. In BGP, we're not directly connected, but a meaningful rule which would be all the routers, all the BGP routers that have learned about the external route through external BGP. So R6, in this case, is the only one. I'm assuming the 18.1 is not coming back through some other path here. If it's not coming back, then the only router that has learned about 18.1 is this one. And it's the only way we can reach this one. So it would make sense that only R6 injects into its forwarding table and puts into OSPF this route here. R2 ideally should not, because R2 has learned about the route through iBGP. It's second-hand information. But this is not what is done in all BGP implementations that I know of. BGP implements directly into the routing table the routes it has. So R2, because it has learned through iBGP of this external route, will put it into its forwarding table. But it will also get it from OSPF. So there will be two injections. There will be a conflict of injection. This is why, sorry, skipping to injection conflicts, we use a fix to this bug, which is called the administrative distance. When a router, if you are curious and you go back to the lab, when you look into the routing tables, you will see the distance to a destination plus something which is called the administrative distance. Administrative distance is simply a number that is saying which protocol wrote this route into the forwarding table. And here we have seen a case where there are two protocols that can write it, BGP or OSPF, and the forwarding distance makes a difference whether it's learned from an internal route that has been learned by iBGP or eBGP. And then you will give what is called an administrative distance, is in fact a priority value. If it's been learned by eBGP, the priority is 20. If it's learned by iBGP, 200, and by OSPF, it's 110. And then if there are multiple routes that exist in the routing table, multiple prefixes, multiple rows that have the same prefix, in BGP it's not possible. BGP will pick only one prefix. But now we have competing protocols, BGP and OSPF, so the same prefix may be written several times, and then this is used as a priority field. So if a route is written by OSPF and by iBGP, which would be the case of the router that has learned of the route through OSPF and also through iBGP, then only the route written by OSPF will be considered because it has a higher priority, higher administrative distance. So that's one of the ugly details that are part of the real world and real life when we do real labs. So in a case like this, R2 will write the destination twice, but the administrative distance will take care of avoiding a conflict. It is as if R2 had not written the route it had learned from iBGP. So because of all those complexities, conflicts, injections, blowing up of the size of the routing tables, some people prefer to not do redistribution of BGP into the interior routing protocol. In this case, only injection is used. So injection is the fact that BGP routers write what they have learned directly into the forwarding table here. So let's assume here we do only injection and no redistribution. So R6 and R2 inject the routers into the routing table. What is the next hop for this route at router R6 and R2? Right. I close the poll. I try to close it, but I've lost the connection to the servers of SpeakUp. We're back. So the majority says B, which is the correct answer that should happen in reality, but it's not the one that happens in reality. But it makes sense. I mean, if I am at R6, I want to go here. The next hop, which I know is this one, so I write it into the forwarding table. If I am at R2, the next hop to go there is this one. So it's the address of R1 East, which is this one here. But we may ask the question, how does R2 know? Right? How does R2 know that this is the address it should put? How would you know? Majority of you said we do this, so how would you imagine this? Well, there's no magic, it's not difficult. R2 has received from BGP the information the next hop is 222. So R2 has taken this course, Tcp-Ip, and says I have to put the next hop into the routing table, and the next hop has to be on link. So I have to go to compute. How do I go to this? How can R2 know how to go to 222? Well, it can go to its routing table and simulate the decision. What would happen if I have to route a packet to 222? I look all the entries I have in the routing table. What is the longest prefix match? And the longest prefix match, if the topology is exactly the one here, is this address, R1 East. So I will put this. Right. This is what we should do in reality. But in order to do that, we've seen that the router had to do some job. It had to process the update, compute a routing decision by going to the routing table. It could have been done in this way, but what is done is not this thing. What the router will do in all practical implementations is to put as next hop 222. So at R2, the next hop will be 222, so none of the above, right? So when I am in a router here, for example, in one of those routers here, I may have a next hop, so to a destination, which is, so in this example, is in order to go to this prefix, I go to 22263 that I've learned from BGP. Then, although it violates what we have seen so far, so that's again one of the differences between the theory and what is done in the real world. A violation is to allow a next hop which is not on link with the machine here. Of course, if you do that, you have a problem, and the problem can be solved by doing, at the runtime, when you have a packet to forward, by doing what is called recursive table lookup. So if I'm a packet, I join this router, and I have this destination address. I go to the routing table, and I see this is my next hop. But in the interface field, there would be a bit saying recursive table lookup. There is no interface because I'm not on link, which means I have to go again to the routing table and look for how to go to 22263, and then I would hopefully find something. Of course, recursive table lookup might fail if there is no entry for this. And this is typically done in BGP routers. If you want, the motivation is the BGP software is lazy. It doesn't want to do the recursive table lookup, so it writes it into the routing table in order to optimize its runtime. Which makes sense in some sense because the BGP is critical when there is a failure. When you want to reconfigure the path, you need BGP to run fast, so you don't want to hog it with this thing. Now, of course, the price to pay is that you have to enable recursive table lookup, which is done in practically all routers. So if we combine those things together, we see that when a packet comes at R2, R2 will have as next hop 2222. So R6 will inject, and sorry, R6 and here we are, R2 injects this into the local forwarding table, and a data packet that goes to this network here, when it's received by R2, will go to R1 here. So, because it will find 222, and then by its own routing table, the entry to 222 works because we have hero SPF that is able to compute all paths to all internal prefixes, and remember 2222 is considered an internal prefix here. Okay? So far, so good. Now the packet joins R1. What will happen at R1? I close in 5 seconds. There was a last-minute change of majority, but anyhow, it is wrong. Let's see what happens. I mean, this packet comes here at R1. Now, what does R1 know? R1 doesn't run BGP. It runs OSPF, but we don't redistribute external routes learned by BGP into OSPF. So OSPF knows only of the internal routes. So OSPF knows how to route to 222, to this interface also, but it has never heard of 18.1. It's not visible anywhere in the topology database or the summary advertisements or any kind of thing inside OSPF. So R1 doesn't know about this prefix, never seen it. So when the packet comes here, the destination address, which is 18.1.1.1, that's the rule of IP. We don't put in an IP header the next hop or the intermediate or something. We just put the destination address. This is unknown to R1. So there will be an error, destination host unreachable. If this one supports sending ICMP host unreachable messages, then there will be a packet sent to the source, but most likely it will silently discard the packet. So the correct answer is it won't work. It cannot be forwarded to R6, right? So in some sense, we have a problem. We said we can do redistribution into OSPF. That will solve connectivity. There might be conflicts that are taken care of by the administrative distance. But if we don't want to do redistribution because it blows up the table, we need to do something else. We cannot simply rely on injecting the routes on all BGP routers because there are also non-BGP routers. So how can we fix the problem? Well, we can avoid that there is no BGP routers. So what is very often done, if you do injection only, you run BGP everywhere, including in this router here. That is not interfacing to any external network. So this is why we find this paradoxical state of affairs that there may be a domain where there are 3 routers, only 2 routers speak to external neighbors, but we still run BGP in all routers, including the ones that are internal. Right? And the reason for that is if we do injection and no redistribution. So in this case, R1 learns from IGP this destination next hop and can inject it in the same way that R2 did it, and that solves the problem. That solves the problem, and this is very often done. Some people find it's a bit ugly, so there are alternatives. What kind of alternatives could you think of? An alternative where you would like not to run BGP in R1, because R1 is a core router. You don't want to load it with the millions of table entries of BGP. If you still want to do a clean thing where R1 does not run BGP, and you would like to not do redistribution, are there other ways that would still work? Any idea? Yes? Updates made by BGP could be sent by OSPF. That is more or less redistribution. That means we put into OSPF all the things we've learned from BGP. And we would use the OSPF messages because we don't want to change the OSPF messages, but we would pass the information. That's redistribution. But redistribution, in some sense, it's right to try to avoid it because you're forcing into the backbone of this domain, for example, that is not interfacing to the outside, you're exposing those routers to all the changes that happen to the outside. For example, if one prefix here that is very, very far away there is no longer routed through this domain, but through this one. Right? For example, there is a long route somewhere through the world, and then due to some changes in topology or changes in policies or a failure, you don't route to 18.1 through here, but through there. Right? Those things happen constantly. They happen all the time here. Then if R1 runs BGP, it will be involved with that. There will be a change of the BGP, will do its recomputation and everything. Whereas from the OSPF viewpoint, nothing has changed. And the external prefixes are the same. There was no failure in the topology, so the interior routing protocol is doing a lot of work because most of the prefixes are external, and whenever they change their next hop, for example. Next hop was here before, now it's there. then it has to recompute this. So it's bothered by a lot of computation due to the external world. And if the internal world is very stable, that's a bit suboptimal. But we could say, once this router knows that the next hop is 222, and he knows it via BGP. That's an external router. It makes sense to run BGP. The problem is that the packet now has to cross this cloud in order to go to 222, but the information 222 has been lost. It's only in the routing table. Is there a way to put this information into the packet inside this cloud? Obviously, yes, there must be a way. This is software. Everything is possible. So, one way to do it, we have seen, is called source routing. We can put a source routing header to this packet. When it comes here, I can say 2.18.1.1, and when this BGP router sees, oh, it's going to a next hop that is not on link, then it can add source routing information 2222, which means that when the router R1 receives this packet, it sees there is destination, oh, but there is a source routing information. So as a router, if I see a packet that has source routing information, I have to look at what is the next thing in this list of places to route to. I don't care about the destination, but first about the next place to send it. The next place will be 222. R1 knows how to route to 222, so that will work. Right? So source routing is one solution to that. Nobody does it, although I've just explained it's nice to do. Source routing in IPv4 is not done. It's supported in theory, but in practice it's not done because it has been used a lot for attacks. If you want to divert traffic and you can inject some source routing information, it's easy to do, so it has a very bad reputation because of that. And also for another reason, which is perhaps more important, why do you think if you are running an ISP domain, you would like to disable source routing immediately? Performance. Performance is one of the key things in the name of which many bad things are done. If you want to run a router, this router, you have to buy a router. Right? In order to buy a router, it's like buying a car. You buy a car or a truck or a train or a plane, or something, depending on what you want to carry, what you have to dimension it. If you build a router, the performance of a router is expressed in numbers like the bandwidth of the link, the bit rate of the link, I mean, how many gigabits are there in the links, and the packet processing capability, how many packets per second can it forward. So the packet processing capability is one of the key figures of a router. And remember, a router is a real-time machine. It receives packets in, has to deliver them as quickly as possible to the outside. Now, in order to make things as quick as possible, you do as little as possible. That's the performance, where performance kicks in. So you're doing as little as possible means, in particular, if you receive an IP packet, you look at the header, and if possible, only at the beginning of the header that contains a destination address and other things. Of course, you can say if you're a NAT, you do other things, but a NAT is typically not in the core, in the backbone of an internet service provider. It is at home, at your place, or at my place. So because of those performance reasons, typically source routing is not used, at least with IPv4. With IPv6, the header have been manipulated in a way that make them easier to manipulate, so that might come when the world is IPv6, but we're not yet there. There is an alternative, which is called MPLS. MPLS, one way to think about it is to think as VLAN labels, virtual LANs. You remember that we have seen that it is possible to decouple where the physical local area networks are from their numbering plans. So we can make a virtual LAN show up in lots of places. And for that, we use virtual LAN labels between switches normally. Now, if you use strictly IP routers, you can't use that. But if you go to Cisco or Juniper and you want to buy an IP router, they will probably offer you that this router can also be what they call an MPLS router. MPLS, multi-protocol label switching. It's another function that routers can do, which consists in forwarding packet not just based on the IP header, but also on a tag, a bit like a VLAN tag, which is called an MPLS label. So if you send a packet, if you support this here, that would mean that if all routers support MPLS, which is typically the case for backbone provider routers, not for small routers, but for backbone provider routers, when a packet is received here, it will be tagged with a label, for example, the label 23. So what is the label? It is a small protocol that exists between the Ethernet, or the layer 2, and IP. So before IP, you put a little tag. You can think of it as if it would be a virtual LAN tag here. Now, when this router receives, so this packet, it tags it with this label. Now, and it sends it to the next hop, which is R1, and the next hop is not given by looking at the IP forwarding table that exists in all those routers, but all those routers have, in addition to the IP forwarding table, a label lookup table where they look at what to do when you receive a packet that has label 23. So if you receive here R1 a packet that has label 23, then you need to know what to do. Of course, you need to set up this operation, but if 23 is associated with the next hop 222, then you can simply look at the label and forward it to the next hop here. So there is some work to do. You need, for every VLAN label or MPLS label, you need to associate a path through the tables that are here to each of the possible destinations. But there are not many outside destinations. There are just as many as there are peering addresses for the BGP routers. So typically when you set up your BGP cloud, you also set up those labels. MPLS is only, that's all we'll say about MPLS in this course. Last year we had a research exercise topic on this, but if you want to know more, I invite you to visit this. Those of you who will take the Smart Grid course will talk about MPLS and the Smart Grid. That's used a lot in different environments. We talked about the injection conflicts. So this is, I would say, how the basic operation of BGP is. We have seen how BGP manipulates paths and has this important concept of AS path. In order to interface BGP and the routing table, we need an important concept, which is the next hop. And we have seen how the next hop is put into the forwarding table, either directly by injection or by redistribution, or very often by both. Now, what we will discuss is how we can implement some policy by playing with the attributes. We've seen that we can implement a policy by not forwarding some routes, but we can do a bit more by playing with the attributes here. Attributes, we have seen some. The next hop is an attribute of a BGP route. The destination prefix is an attribute. The AS path is another attribute. So those three attributes that I've just mentioned are, of course, mandatory in every route. Now, in addition, there is a large number, several tens of possible attributes that are just here to facilitate the design of a policy. One of them, which is very, very easy and very often used, is a priority field called local preference. A local preference is something you can configure in all your BGP routers inside a domain by having an access list that says whenever you receive something, you analyze what's some route, you analyze the different fields of the route, and you tag it with a local preference. For example, in a case like this, I can have two routers, R6 and R1, that are connected to the outside world, and you may decide to give whenever you receive a route from the outside, R6 might decide to give it a preference of 100, and R2, or with R2 a preference of 10, which means that inside this domain, the highest preference would take priority. So which would mean that the routes received here would be preferred over this one by the decision process. We've seen that the decision process considers a number of criterions: length of the AS path, distance to IGP, distance to destination, whether it's eBGP or iBGP. If you want to supersede all those rules, you put a local pref value. So if you put 100, it means it's preferred, and you don't even consider all the other cases. Here is an example, a practical example. AS4 peers to AS2 and AS3, but doesn't like AS2 very much, or thinks that AS2 is very expensive, so would normally not like to use it, but since you never know in the world of BGP, you want to have backups, so you still peer to this guy. Then what could you do? Well, when A4 would set local pref to 100 to all routes received from AS3, and to a lower value to all routes received from AS2. That's a simple way to say, I prefer to use AS3 whenever I have the choice between AS2 and AS3 here. So R1, where is our R1 here, receives, for example, the route AS2, AS1, 10.1, so this one here. It will set the local pref to 50, and R2 will set the local pref to 100, because R2 knows that it is coming from AS3. So this you have to program through the access control lists and the maps you put in the routers. Once you have done that, what will R3 announce to AS5? I close the poll. And the correct answer, which is the majority vote, is B. So router R3 will receive two routes from iBGP to the same destination. One that has preference 100, this one that has preference 50, this next hop. R3 will select only one. And here, it's very simple. You select the one with the highest preference, so you will pick this one. So you will pass to AS5 the route that receives here. So AS5 will not see at all this AS path for this destination. But of course, both have been received, so if there is a failure somewhere, they are remembered and will be reused. Right. Local pref is used inside a domain, so it's propagated by one router to another one, and it's a way to, it's a very simple way that is perhaps the most of all the attributes, the most used of all the attributes, to implement a given policy about which AS you prefer over which other one. There are other priority fields, for example, the wait, but the wait, contrary to the local pref, is only local to a BGP router, so you will never see it in a BGP message. Yet another priority field, which is very specific to multi-homing, is called the MED, multi-exit discriminator. And the difference with the local pref, it's like a local pref if you want, but a one that is passed to an outside peer. So it can be used in eBGP. So an eBGP message will always make sure there is no local pref in there. But the MED can be used. So the MED is used here also to signal a preference. And it occurs in a case where typically you have what is called multi-homing. Multi-homing is something that is a very hot topic in the internet because it doesn't work very well, but is something that is very desirable by all customers of internet service providers. If you connect to Switch, for example, but you have, I don't know, a presence somewhere in the Emirates or somewhere else in the world, perhaps you want to connect to another provider somewhere else because of geographical, if you connect to Switch sorry, I said something wrong. This is not a multi-homing issue. This is you're connecting to the same provider, but at different places here. For example, EPFL might connect to Switch in Lausanne and in Sion or in Neuchâtel in different places here. So this is a very typical case for any company that is connected, has multiple sites and is connected to a single ISP here. Then you would like to give the information which preferred link you would like to use. So for example, if there is traffic going to 10.1, perhaps you would like to signal to the provider X that you would prefer traffic to 10.1 to go this way. So how do you do it? You put a priority field. Now the embarrassing thing is that here for local pref, the higher the better. For MED, it's the other way around, the lower the better. So MED 10 means it's preferred. So you would advertise to X the two prefixes, We saw that we can do one or the other depending on how we decide to originate the routes. But it's a good idea to do both just in case something crashes somewhere. So here, this BGP router advertises 10.1 and also 10.2, which is here. But the intention of this customer is that all traffic to 10.2 should go through the provider to 10.2. Because after all, if you're using a provider, you would like the traffic to go here. Perhaps there are still internal links. I don't think there are internal links, but I'm not even sure, between Sion and Lausanne. Assume there is one. We have a leased line of some kind for some traffic here. You would still like to use it only for dedicated purposes, but you want most of the traffic that goes from the outside to here goes via your provider, not through your internal line. That's a choice. You might have the opposite choice. We've seen that we can prefer to use our own links as transit, or in contrast, use a provider link as transit. Typically, if you pay someone to be a provider to you, you want them to be the transit for you. So if you do that, you will use the MED here. And let's see more. So now we are at R1. R1 receives from R3 those two routes. And one also, R1 is to from R3, and one via R4 learned from R2 by IBGP with MED equal 10 here to the prefix 10.2. What will the decision process at R1 do for this prefix 10.2.16? I close the poll. And the majority is right. The solution is in the decision process. You look at the decision process and you will find that one of the criterions is the MED. All others have similar, an MED comes before. So you will, at R1, you will prefer this one because it has a smaller MED 10, which is the intention of MED. You want to signal to a provider that you prefer to use this exit rather than this one. Well, we will not go in detail through all the attributes that are mentioned here. There are a few ones that I'll let you discover. And as you can imagine, there are multiple ways to combine the attributes. And there are multiple choice of attributes that can lead to a given desirable policy. So here is one example. Back to our very first example explaining policy last week, I am ISP1, right? Assume ISP1 does not want to use the link ISP2, ISP3 for transit because it has its own links and it wants to give a better service to its customers. So it would not like to do that, right? However, it's still a good idea to use it as backup. Even if you're a good provider, even good people have computers and routers that fail, right? So here might still be a problem. There might still be a loss of connectivity internally. So you might still want to use that if nothing else works. If, for example, if your BGP router here crashes and it takes 15 minutes to recover it, then during those 15 minutes, you are happy to have an alternate path here rather than no path at all. Right? How could you do this with all the elements we have seen so far? Right. Any idea? So you would like to accept all the announcements that are received from ISP2 and ISP3. For example, if you receive a route for a prefix in C3 that has an IS path ISP2, ISP3, C3, you would like, before in the policy that I explained before, you would reject it. You say, I don't keep it. Right? If you want to be smarter, you want to use it only if strictly necessary. What can you do? Any idea? then if nobody has an idea, I'll let you think about it and read the solutions that I will post in a few minutes online to see how you could do it. Voilà, that's all for today. See you tomorrow.